In this lesson, we're going to be looking at some of our other trigonometric ratios. We've already looked at sine, cosine, and tangent, and today we're going to look at a couple more of these special ratios that we have that relate the angles and the side lengths. Okay, so these are just in addition to sine, cosine, and tangent, and these are not used quite as much, and really we can easily go back and forth between these three and our sine, cosine, and tangent, and really that's what we have to do in order to plug these into the calculator, which we'll see momentarily. But the three that we're looking at today are cosecant, secant, and cotangent. And the cosecant is just the hypotenuse over the opposite side. So the length of the hypotenuse over the opposite side. Secant is the length of the hypotenuse over the length of the adjacent side. And the cotangent is the length of the adjacent side over the length of the opposite side. And as we look more closely at this, this should resemble really our sine function. Remember, sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite. So it's the same thing, except we've flipped this thing. So this is very similar to sine of theta. So when we think about these, think about them together. Okay. Same thing with the next one. If I look at the next one, this should seem very, very familiar. This is very similar to our cosine of theta. So when we think about secant, secant is hypotenuse over adjacent. Well, that's kind of like cosine, except it's been flipped. Cosine was adjacent over hypotenuse. Okay, so again, think of those together. And then the last one, cotangent, really that's related it's very similar to our tangent function. Remember, tangent was opposite over adjacent, and now cotangent is adjacent over opposite. Okay, so really it's kind of very similar to what we already did. These are pretty much the same thing, except we flip each of these ratios. Okay, so sine flipped is cosecant, cosine flipped is secant, and tangent flipped is cotangent. All right. For example, so again, easy way to remember these: just remember the standard trig ratio, and then remember which two are related, and then flip them. Okay, so for this one, if I want to I'll list all the trig ratios for A and B, and really just the trig ratios that are listed above. So I'm going to start with cosecant. So cosecant of A. Remember, cosecant is essentially the same thing as our sine, except flipped. So if we're looking at A here, the sine would be opposite over hypotenuse, would be 10 over 26. So the cosecant would just be the opposite of that, be 26 over 10. All right, which is 13 over 5. And that's it. Okay, that's all we have to do for that. Likewise, if I did the cosecant, let's jump right to the cosecant of B. Well, the cosecant of B, now I'm looking at this guy. If I'm looking at angle B, this is just like sine, except reversed. Sine would be opposite over hypotenuse. So this one's going to be hypotenuse over the opposite side, which is going to be 26 over 24. Which, of course, reduces to 13 over 12. Okay, so I've got my cosecants, really just like finding sine, and then we flip each of those. Okay, if I move on to secant next, our secant functions. The secant of A, again, if I'm looking at angle A, really it's the same thing as cosine, except we flip it. Cosine would be adjacent over hypotenuse. So instead, now I'm going to do hypotenuse over adjacent. So I'm going to do the 26 over 24. And now if I do the secant of B as well, when I do the secant of B, again, if I look at the B right here, cosine would be adjacent over hypotenuse. So instead, I'm going to do hypotenuse over adjacent. I'm going to do the 26 over 10. So really, it's just a matter of tying it to that original trig function and then flipping it. So that's 13 over 5. And you should notice the special relationship that we have here. It was the same as the special relationship that we had between sine and cosine. When you look at cosecant of A, it's the same as secant of B. And when you look at cosecant of B, it's the same as secant of A. And that was true with our sine and cosine as well. All right. And then last, we've got the cotangent. So the cotangent, again, if I start off with something like A, I'm looking at angle A, tangent would be opposite over adjacent, so it would be 10 over 24. So cotangent is just that flipped. It's going to be adjacent over opposite, so it's going to be the 24 over 10. All right, and when I divide each of these, when I simplify, it's just 12 over 5. Okay? And now, of course, my cotangent of B Forgot to put the little b in there. Oh, I missed this one as well. Let me try that again. This one's cotangent of A. This one's cotangent of B. Again, if I look at my B, if I look at this angle, tangent would be opposite over adjacent, but now instead I'm going to do adjacent over opposite. So it's going to be the 10 over the 24. And just like tangent had a relationship where when we looked at one angle, it was the same as the other angle except flipped, and the same thing here. Cotangent of A and cotangent of B are the same thing, just flipped. And so really what that should tell us then is cotangent of A is the same as tangent of B, and cotangent of B is the same as tangent of A. Because really, that's the relationship that these have. Cotangent is flipped. Well, that was the relationship that the two tangents of the two angles had as well. Okay? So getting into some examples of these, really, the big idea between these examples is the only sine functions I have on my calculator are sine, cosine, and tangent. Okay, those are the only trig functions, sorry, that I have on my calculator, sine, cosine, and tangent. So really, when we approach these, if I have something like this, if I have sine of theta equals 0.5, what's the cosecant of theta? And so when you think about cosecant and sine are essentially the same thing except flipped. So let's write this as a fraction. If cosine of theta is 0.5, which is 1/2, that means the cosecant of theta would be 2 over 1, or really just 2. Okay, and so we just gotta kind of understand that relationship and bounce back and forth between these things. And really, when I want to plug these into my calculator, I always want to write in terms of sine, cosine, or tangent. For example, and so when I look at something like this guy, if the secant of theta equals this, we want to find the value of theta. And really, the issue here is normally I would just do an inverse trig function on my calculator and undo the secant, but there is no inverse secant on my calculator. There's only inverse sine, cosine, and tangent. And so really, secant is related to cosine. I know that the cosine of theta is going to be the same thing but flipped. The cosine of theta would be root 2 over 2. And the reason for that, when you look at this, secant is really the hypotenuse. This is a hypotenuse over the adjacent side. Well, the cosine is adjacent over hypotenuse, so I just flip it. And now from here, I can plug this into my calculator. I do the inverse cosine of each side, and that'll allow me to solve for theta. Okay, so I go ahead and I plug that into my calculator, and I find out that theta equals 45 degrees. And that's it. All right. Same thing with the next one. The cotangent of theta equals 5 over 4, and I want to find theta. Well, let's change it to tangent. So this is going to be the tangent of theta equals 4 over 5 instead. And really, all I'm doing there is essentially saying, okay, well, cotangent is adjacent over opposite. Well, now opposite over adjacent would give me 4 over 5. So I'm identifying each of those sides. And now I just do the inverse tangent of each side. And now it's just a job for my calculator. So when I plug that in, it gives me approximately 38.66 degrees. Okay? Same thing with the next one. I've got a secant once again. And with this one, the secant is the same thing as cosine, essentially, but flipped. So I'm going to do the cosine of theta equals, now I'm just going to do root 3 over 4. Once again, I'm going to take the inverse cosine of each side, and I don't think there's any need for me to write that out anymore. I'm sure we're probably getting used to this, but I just plug it into my calculator and I find out that theta equals, looks like a 64.34 degrees. That's it. All right. A couple more kind of varied examples here. If I have something like this, the cotangent of theta is 4 over 3, and I want to find a possible length of the hypotenuse. And so really this just causes me to draw a picture here. If I were to draw a triangle and call this theta, all right, well, cotangent is adjacent over opposite, so the adjacent side is 4, the opposite side is 3. And really, it's just asking me to find a possible side length. And keep in mind, it says possible side length because I could make this like a 6 and this one an 8. okay? Because really it's a ratio that's been reduced. These could be any multiple of that. But now if I find any one of these possible sides, really it's just my Pythagorean theorem. So I do 3 squared plus 4 squared equals c squared. And what I find out is this is actually going to equal a 5. Or it could be some multiple of that. It could be something like a 10, all right, depending on what I have here. So 5 is a possible side length if I use side lengths of 3 and 4. If I use something like 6 and 8, now I'm looking at a side length of 10 for my hypotenuse, okay? Same thing with the next one. Again, if I just draw a quick triangle here, and I label one of these as theta, well, secant of theta, again, secant is the same as cosine, so we're talking about adjacent to hypotenuse. Cosine is adjacent over hypotenuse, so this one is hypotenuse over adjacent. So my hypotenuse here is the square root of 6. My adjacent side is the 2. Now I just need to, once again, use my Pythagorean theorem in order to solve this thing. And so what I'm doing here is, I could call this a, so I'll say a squared plus 2 squared equals 6 squared. So what I actually end up with here, let me just write it out. This was just a little bit trickier, but 2 squared equals square root of 6 squared. And so what I end up with is a squared plus 4 equals 6. So I find out that a squared equals 2. So I take the square root of each side, and I find out that my missing side here is the square root of 2. All right? And again, that's just one possible answer for this. These are ratios, so this could be a 4. This could be 2 root 6, all right? Or I could multiply each of those by 3 and have another ratio, and then the a value over here would also be multiplied by 3, all right? But it's asking me to find a possible solution for this. Well, there's one possible solution for finding the missing side, all right? So just by taking these ratios and understanding whether it's opposite or adjacent or hypotenuse, labeling them on the triangle, I can then use my Pythagorean theorem to solve for the missing side. But again, cosecant, secant, and cotangent. Cosecant is just like sine but flipped, secant is just like cosine but flipped, and cotangent is just like tangent but flipped. All right, and we're going to continue to use those in different capacities, but really the idea is to relate them back to sine, cosine, and tangent so that we can start solving these things. Okay?